So this will be part 5 of section 4.4, and in this video I'm going to try and set up the rest of the problems, 18 through 30. We'll see how far we get. So number 18, we're doing another box cut out of a flat piece of cardboard, but this time we're doing a little bit differently. So I'm assuming you're familiar with the problem, and I've drawn a sketch of the picture here. So once again on 18, they have me go through lots of parts. Part A, write a formula for the volume of the box. B, find the domain. C. So let's just sort of tackle this all as one problem. So we're going to fold this all up and make a box. And we know that the volume of the box is going to be found by doing the length times the width times the height. And so we'll say this is the length from here to here. So we're going to figure out what that is. The entire length is 15, and we've taken away an x right here, and we've taken away an x right there. And then we have this length and that length left over. So if this is what we're going to call L, and this is L, then I know that L, or we could write 2L plus 2x equals 15. Or in other words, 2L equals 15 minus 2x. And then we divide by 2 and I get, we'll just do it individually, 15 halves minus x. So that's your length. Your width will be easier. It's just 10 minus 2x. And then your height of the box will again just be x. And so then as you go through the problems, part A, write a formula for the volume of the box. We're going to want to distribute and clean this up, but we've done that. Part B says find the domain of the volume of the box. And so once again we have to think about this. X has got to be bigger than 0. So domain is going to be, technically we'll let it equal 0, and then the volume would be 0. And then if x is 5, that'd be as big as we could go on this side, but the question is, what about this side? If x is bigger than something, are we going to have a problem? And really the answer can be found right here. 15 halves minus x, 15 halves is 7.5. So if x was 7.5 here, our volume would be 0, but 5 would come before that. So 5 is going to be our issue. So I think we can safely say that the domain is 0 to 5. All right. So then it says use graphing to find the maximum, confirm it analytically. We'll do the analytically part first, but we'll do that in a separate video. So again, here's the volume equation. We simply want to maximize it. All right. So then we get to problem number 19, which is another box question. And this one is definitely chopped up a little bit unusual, and if you haven't taken the time to look at this question and really study it, then you really should stop the video and do that now. I'm going to proceed with the understanding you have read this question thoroughly. So this box is created a little bit differently. The base of the box is going to be right here, and then the height of the box would actually not be x anymore. It would actually be, we'd be folding along this line right here. So if we fold along this line, then this length right here is now vertical, and this piece right here is in fact going to be your height. So we'll need to figure out what that is. So we'll have the length would be here, the width would be here, and the height would be actually here. All right. So volume of the box, length, width, and height. And again, I'll say that here's length, here's width, and there's height. Okay, so now we got to write these pretty much in terms of x here. So volume is equal to length. If we're cutting out an x, a little square right here, there's your x square, and there's your other x square. So that would mean that we've cut out x and x, which is what the length would be. So the length of that base is going to be 2x. The width is going to be simply 24 minus 2x. And now the height is going to be this length right here. And half of this 36 box, if we sliced it right down the middle here, we've got 18. And of that 18, we have part of it is x, another part is x right here, and then this leftover piece would have to be the height of the box. And so we get ourselves 18 minus 2x would now be the height. So take your time and look that over, because that might be really hard to tell, especially from my really pretty god-awful picture. But if you look at it in the book, I think you'll see what I've got here. And number 19 asks you lots of questions. Write a formula for the volume. This is part A. Part B, find the domain. And again, the domain can really be found by looking at what makes the volume 0. So x is 0, clearly is our small. If x is 12, my volume is 0. If x is 9, my volume is 0. And if you look at the graph of the volume, what it would look like, it would be a cubic function with a 0 at 0, 9, and 12. We know it's a cubic function because as I multiply this all out, we're going to get x cubed. And this graph is actually going to look something like this. So clearly volume has to be positive. So any of these values under here really don't make any sense. And that's really why our domain is simply going to be from 0 to 9. As x is 0, the volume is 0. As we let x get bigger, my volume gets bigger until I reach a certain point, which I'm really looking for. And then as I get closer and closer to x is 9, then our volume goes back to 0. Then the volume heads to negative, which doesn't make any sense. And this is because now we're bigger than 9, and I can't cut more than 9 out of 18. So the problem really falls apart past 9. And that's why our domain is simply between 0 to 9. And then we just go through and we multiply this volume out and then take its derivative, etc., etc. So we'll possibly come back and solve that in another video. And then we get to number 20. So once again, I'm assuming you've read the question. We're in a boat out here, and we want to get back to the village. So we want to get there as quick as possible. And so what this really is going to come down to is, it says, where should we land the boat to reach the village in the least amount of time? So what it comes down to is we're going to have a time equation, and whatever we come up with for that, we'll have to minimize it. So let's think about how we could get to the village. We could take our boat and we could row directly to the village and not walk at all. And that has an advantage in that the shortest distance is a straight line. So a line segment connecting from here to here would represent the shortest distance. So that seems like a good idea. Except when you take a look at the question, and it tells us that we can row 2 miles an hour, but we can walk at 5 miles an hour. So we can walk faster than we can row. So with that logic, it might seem that maybe instead of rowing straight there, we should get to land as quickly as possible and then walk over. So maybe we go directly there. Maybe we go straight into shore and then walk the whole way. That has the advantage of now we're walking more, which is faster, but that's also going to be the longest trip possible. So we came straight in and went straight out. That's the longest journey we could take. So what I want to do is let's make an assumption. Let's make an assumption that the answer is going to be somewhere in between. So I'm going to point my boat and row somewhere to shore, knowing that going straight there probably isn't the answer, and going straight to shore probably isn't the answer. So what I'm going to do is I'm going to undo that line, and I'm going to row to this point right here. It's this arbitrary value. And what I need to do is I need to give it a name. So we may want to come back and change the labels in a little bit, but let's just start someplace and see where we get. So let's say that I'm going to make this distance x. And x represents the distance from going straight in, so being 6 miles out, the distance from going straight in to where I actually land. I'm going to call that x. So then that would make the distance from here. I mean, you could give it another variable if you want, like y, but ultimately we'll just have to change that because we're going to want one variable. So if this is x, notice the whole distance here is 6, so this becomes 6 minus x. Okay, and if this is x, we know 2 miles out, so this is 2. That would mean that the distance from this point to this point is the hypotenuse, and so we can find that doing 2 squared plus x squared equals, let's call this y for now, equals y squared. Or we could say that y is equal to the square root of 4 plus x squared. So we wrote it as y, but really I know what y equals in terms of x's, so I think it makes sense if we replace this y with the distance in terms of x, which would be the square root of 4 plus x squared. Okay, so if the question just said let's minimize distance, then that'd be a lot easier question. To minimize the distance, we would just row straight there. But it says minimize the time. Okay, so now let's break up time into the different components. What are we going to be spending our time doing? So part of the time I'm going to be rowing. So let's say time little r, time rowing, plus time walking. So let's call it time w. So those are the two activities I'll be partaking in, and I want to add those two times together to get the smallest time possible. So now it simply becomes how do I turn these times into the variables that we're dealing with in this problem? Okay, so anytime we're talking about distances and time and then looking in the problem the rates, I always think, of course, of distance equals rate times time. So I want to solve for time. So let's set this up and let's make this be time rowing. So let's change this to TR. So let's plug in what we know. Assuming this situation, what's the distance we're going to row? It would be the hypotenuse. So that would be the square root of 4 plus x squared. The rate I'll be rowing is 2 miles per hour times the time I'll be rowing. So time rowing equals the square root of 4 plus x squared over 2. And then time walking is going to be the distance walking equals the rate walking plus time walking. The distance I'll walk, according to the setup here, is simply going to be 6 minus x. The rate I'll be walking, and this is a times, not plus, the rate I'll be walking is 5 miles per hour times time. So time walking equals distance divided by my rate. And so now I can write my total time as a function of these two times. So time rowing, 4 plus x squared over 2 plus time walking 6 minus x over 5, and that's it. So now, if you'll notice, I have a time equation whose only input is x, the distance I decide to row toward shore. So we're going to solve this problem, and maybe we find that the minimum time is when x is 0, and that would tell us that we should not aim down shore, we should go straight in and then walk. But if we find that maybe time should equal, x should equal 6, if that's what we find, then that would be rowing straight to the village. So I suspect our answer will be somewhere between 0 and 6. Well, I know it'll be between 0 and 6. The question is how far away from the endpoints. So this is clearly going to be a somewhat unfriendly derivative to take, but that's all I need to do is take the derivative and go from there. All right, how many problems do we have left? 26, 29. Okay, we've got several problems left. So I'm going to stop this video because it's getting too long, and we'll do setup of 26 next.